All right, continuing on here. Um, as I mentioned, this was done as a homework assignment for 415. So here are a whole bunch of comparisons of the different numerical methods that I mentioned. And one of the things that was to be done in the assignment was confirmed that that the Euler method doesn't work. It as even with a really small time step, the Euler method, A, doesn't conserve energy. It's not being shown here. But B, it doesn't produce a closed orbit. Whereas Verilet's clearly, even with a much bigger time step, makes a nice closed orbit and conserves energy. Um, um, here's the sun and the earth with realistic masses. There's our energy, which is a very nice -20. Negative energies mean that they're bound, and it's conserving energy quite well. Here's an interesting uh, uh, three-body problem called the Montgomery orbit. This is a very, very special set of initial conditions that make for a stable three-body problem. There are not many stable three-body problems with closed orbits like this. And I've done this both with the central and the non-central situation. And here, just to show you the difference, if I change the initial conditions by parts per million, uh, the solution no longer makes these nice closed orbits. They drift away from this nice closed orbit with it kind of moving gradually further and further from this nice figure 8. And at some point here, we actually have this collision sort of, and then things get blown apart as they come too close to each other. So other ones, here's N-body problem with a whole bunch of planets orbiting this central star in here. Energy is being conserved pretty well. It's negative. This is bound. And here it is with the planets running into each other. So they're coalescing. Now, you notice this is way more expensive. I've got close to 1,000 particles starting off here. My frame rate is abysmal. And I think you'll see here as they collide and stick to each other and get bigger, down here around 400, it starts to speed up appreciably. And now I have just a handful of big planets going around this central sun that still has many planets getting sucked into it. So all that's very, very cool. There's a situation where what happens to the solar system if another star comes by too close. And there's also a menu system that lets you set up the different parameters. You can set the velocity, the planner, how many planets there are, what the sun mass is, and when you're ready, you press play, and it goes ahead and makes a little solar system of that ilk. So all this is very cool, and I'll let you play with these. Oh, there are two other ones. There's a solar system with asteroids, and the asteroids fast takes into account that asteroids weigh hardly anything compared to the actual planets. And so the efficiency here is that I'm only doing an N-body problem, the influence of the planets and the sun on the 1,000 or so asteroids that I have. And so even so, it runs a little slow, but this is not a full N squared body problem, but it is interesting. And if you watch this to completion, you'll find that most of the asteroids end up between Jupiter and Mars, which I think is an accident, perhaps, but still intriguing. So I'm going to stop there. I'll stop sharing and I'll end recording, and I'll see you all in class. Bye.